Hi there, welcome to this video. My name's John. I provide mathematics tuition for A-level maths, A-level further maths, 6th-term examination papers and mathematics admissions tests. Very warm welcome to this video where we're going to take a look at a problem that I've selected from a 6th-term examination paper, and in particular we're going to look at the Step 2 paper from 1990 and question 12 from that paper. So this is one of the mechanics problems from that particular paper. I'll leave a link in the description to this video so that you can download the paper yourself, and also during the course of the video at various times I'll put the question up on the screen so you can see it as well as you're watching the video. Okay, so don't be concerned by the fact that we're going back to an old set paper here. So 1990, obviously the maths and further maths specifications have changed since 1990, 35 or so years ago. Don't be put off by this. If you are preparing for a step paper, the best advice that I could give you is just be prepared to go beyond the specification. Okay, be prepared to expose yourself to unfamiliar ideas. That might mean that you've got to learn about some techniques that are not on the current specification for A-level maths and A-level further maths. Now, I'm not saying that, strictly speaking, you need to know these for your step. It's just really, when it comes to, if you're going in for a step paper, then chances are you probably already know how to, for example, find the nth roots of a complex number and solve quadratic equations and differentiate using the chain rule and all this kind of stuff. You know all that stuff. The main thing that you need to be working on when it comes to preparing for a step paper is your problem-solving skills. So you develop your problem-solving skills through solving challenging problems. And those challenging problems will usually, if they're genuinely challenging, will involve things that you're slightly unfamiliar with. That might mean non-specification material, where you've actually got to learn about something new in order to solve that particular problem. Okay, and this is all good for developing your problem-solving skills. So it shouldn't be a concern to you if you are preparing for a step paper. If you're looking to go into university to do mathematics, for example, it really shouldn't be a concern to you to go beyond the specification. Really, you should be enjoying learning about mathematics, whatever it looks like. If, however, you do feel that you are concerned about learning non-specification material, all I can say is that might point towards the fact that your heart's not really into learning mathematics, unfortunately. Okay, so before we get onto the question itself, just a few comments that I want to make. So clearly this video is a different style to the videos that I've been uploading previously. So in the videos that I've been uploading over the last couple of months or so, I've been using the whiteboard quite extensively because that's all I had available to me at the time, and I wanted to make some videos, so I just made do with what I had. But I noticed that it was kind of difficult in some of the videos to see what I was writing on the whiteboard sometimes, so I've got a new writing pad so that I can write and it appears on the screen. Hopefully it will be a bit clearer. You'll be able to see what I'm writing a bit more clearly. My writing's still scrappy, so that's something that you'll just have to deal with. There's nothing I can do about that. But I'd be really grateful for your feedback on which you prefer, whether you prefer me using the whiteboard or whether you prefer me using the writing pad, or if there's anything else that you think I could try to make my videos a little bit more clear. Okay, so let's get into the problem without further ado. So there's quite a bit of information here. Always make sure that you understand the information that you've been given. It's surprising, it's bewildering to me even, how many people will still try to jump into solving a problem that they don't even understand. You can't do it. You can't solve a problem that you don't understand. So with the information, just make sure that you've given yourself sufficient time to thoroughly process that information, at least enough so that you've got a good idea what it represents, and that you're in a reasonably good position to actually start trying to solve the problem. There's no point, if you don't understand something, really it's going to be very difficult, if not impossible, for you to solve that particular problem. Use diagrams, be organized with your working. Okay, anyway, let's get on with things. So question number 12, step 2, 1990. A straight staircase consists of n smooth horizontal stairs, each of height h. A particle slides over the top stair at speed u with velocity perpendicular to the edge of the stair, and then falls down the staircase, bouncing once on every stair. The coefficient of restitution between the particle and each stair is e, with e less than 1. Show that the horizontal distance d sub n travelled between the nth and n plus 1th bouncers is given by the following expression. So I'll write it on the screen so that I can get warmed up. So we've got d sub n is equal to u times 2h over g to the power of a half e alpha sub n plus alpha sub n plus 1, where alpha sub n is equal to 1 minus e to the power of 2n over 1 minus e squared to the power of a half. Okay, so all of that information is going to be relevant at some point during this calculation, during this the solution to this problem. Okay, things to really pay attention to initially is that we've got smooth horizontal stairs, each of height h. The particle slides over the top stair at a speed u with velocity perpendicular to the edge of the stair. Later on, it's going to be important that the particle falls down the staircase and bouncing once on every stair. So not all of these bits of information are going to be relevant straight away, but just so you know, all of these bits of information are going to be relevant at some point, and hopefully I'll remember to point them out as we go along. If there is anything, by the way, that you don't understand in this video once we're finished, just ask in the comments section. Okay, that's what I'm here for, to help you guys prepare for your STEP exams, your MAT exams, your A-level maths and A-level further maths exams. Just ask the question, okay? This video might be a little bit more protracted than some of the previous ones that I've done because I'm still getting used to this technology. I'm still finding my way around. I'm still getting my bearings and everything. So just bear with me. If I need to, I can always remake the video further down the line, but just bear with me on this one. I'll give it my best shot. Okay, so before jumping straight into finding d sub n, what I found useful here, and the whole point of this video is for me to explain to you, to describe to you what the problem solving process looked like for me as I was trying to solve this problem. This is not meant to be a model solution. Don't take this as attempting to be a model solution, because it's not. If you want a model solution, something that's going to be a bit more refined and to the point, watch another video on this, or if there is a mark scheme, look at the mark scheme. I don't actually know if there's a mark scheme, so I don't look at them. But check that out for yourself, because this is what I'm going to be doing here. Is I'm going to be describing to you the kinds of ideas that I was having, the approach that I had to solving this problem. If you don't like the video, don't watch it. It's as simple as that. So the reason that I want to do this is because what I find is that a lot of people at A-level have some real difficulty with getting their heads around the problem solving process, because in their textbooks, in the classroom, everything's presented, all the solutions to problems are presented in nice, refined, polished forms. Okay? And it's not necessarily made clear that that solution may be the product of a lot of effort and a lot of trial and error and a lot of kind of false starts. Okay, so sometimes you have an idea, you try it, it doesn't work, you have to try something else, and eventually you find something that does work, but it might be after several iterations. And this is a normal part of the problem solving process, but because people seem to see problems just being solved first time every time in kind of this polished, refined, perfect sort of way, they think, oh, I should be able to do that, and that's just not the case at all. So I'm trying to give an idea, I'm trying to capture some of the messiness of the problem-solving process, and some of the difficulties that you might encounter, and some of the kinds of strategies that you might use to overcome some of those difficulties. Okay. So, when I attempted to solve this problem, the first thing that I did was to draw a diagram. Okay. So, let's draw a diagram, try to represent this situation. Okay, so my stairs are not exactly squared away, but never mind. So the height of each of these stairs is going to be h. And initially the particle is projected over here. It's effectively projected with a speed of u meters per second horizontally. And I'm going to take the time of projection to be the instant where the particle leaves this top step here. Okay? That's effectively for me when t is equal to 0, if I need to set a t equals 0. The stairs are smooth. There's no friction. Okay? What kind of a trajectory does this particle follow? Well, it's going to be free fall or motion under gravitational force only. So it's going to follow a kind of parabolic path. Like this. There's a button that I keep pressing on this pen that makes the screen flicker. So the ball bounces. So obviously it's going to bounce up a bit. And then it's going to come back down. It's going to bounce on the next stair. Then it's going to bounce up again. And it's going to go down. It's going to bounce on the next stair. Okay, so obviously this is the first bounce. This here is the second bounce. Oh, second bounce. Okay, so I can see now what this situation looks like. Okay, I can imagine it in my head. I can imagine this particle, this ball or whatever it is, bouncing down these stairs. But what I really want to know is, how is this going to work algebraically? How is the story going to progress in a kind of algebraic sense? So what I did initially, and you might not need to do this, is entirely up to you. What I did initially was to find expressions for D1, and I think I went so far as to find an expression for D2 actually. So I've got my notes here just to refer to if I need to. Because I wanted to go through the calculations between each of the bounces just to see kind of how the algebra was developing. Okay, it turned out that actually I didn't realize it initially, but actually these calculations were eventually going to form the basis of the calculation that I ended up doing to prove Dn. Okay, first of all, initially all I was trying to do was just kind of familiarize myself with the situation a bit more thoroughly, and to try to get some kind of insight into how this formula Dn might come about. But it turned out that, especially the formula that I got, the equation that I got for D1, turned out to be very important actually further down the line for me to use. So these are going to be Suvat calculations. Now the Suvat equations are going to be valid between, say, the point of projection and the first bounce, and then between the first bounce and the second bounce, and then between the second bounce and the third bounce. But the Suvat equations are not valid for the entirety of this trajectory. Okay, we've got to take it between the bounces, effectively, for the simple reason that as the ball bounces, it's not constant acceleration. Right? We can't model that as constant acceleration. we can model only as constant acceleration between the bouncers, or between the time of projection and the first bounce. So it's going to be suvat, and it is, because there's only gravitational force involved here, then it is suvat that we can use. This coefficient of restitution, E, is really applicable to... So we've got the horizontal stairs. So that means that the velocity of the particle at each point is going to have a horizontal component and a vertical component. The coefficient of restitution really applies to the vertical component of the velocity. Okay, in other words, in a direction perpendicular to the stairs. Okay, if we take the horizontal part of the stair, the coefficient of restitution applies in a line that's perpendicular to those stairs. So the speed of this object in the horizontal direction is going to be constant. There's no forces acting on it in a horizontal direction. The coefficient of restitution doesn't affect anything in the horizontal direction. So the speed through the horizontal speed throughout is going to be constant at u meters per second. So what I tried to do initially with this was I was going to use suvat equations, but I was going to try and use them in a vector form. So we've got, for example, we might have something like S equals ut plus a half at squared, or v equals u plus at, something like that. And we'd have something like u is equal to u0 meters per second, and acceleration is equal to 0 g meters per second squared. But I thought this was going to be a bit cumbersome, a bit clumsy, and it was going to be a bit overkill actually, because I didn't necessarily want to involve the horizontal component of the velocities, or consider the horizontal direction that much really. It was really the vertical motion that I was interested in. So what I found was better to do was to actually split the motion into the separate horizontal and vertical components, and just look at them separately, and just do suvat in each direction separately, rather than trying to do everything in one go using the vector forms. So let's get rid of these. We're not going to be using that. But the point is that sometimes you just don't know. You've got to consider something before you can discard it. And it's part of the problem-solving process. So to use suvat equations, I need to decide on some positive directions. So throughout this problem, I already kind of hinted at actually in what I've just written with the vectors for u and a and things like that. I'm going to take... That's not very down. That's not very good, is it? I'm going to take downwards as positive in the vertical direction, and I'm going to take left to right as positive in the horizontal direction. So that's going to be consistent throughout my solution to this particular problem. Okay. It might be worth you taking notes as well, because I am going to have to change the screen, so I can't necessarily keep everything on the screen all at the same time. So I might have to refer to some bits that I've already written out that are not on the screen anymore. Sometimes I will scroll up and down, but it just takes time. I'd rather not if I don't need to. Okay, so what I did then was to look at the motion between the vertical motion in particular, between the point of projection, the time of projection, and the time of the first bounce. Now, importantly here, stay organized. Find your own way to stay organized. How you do that is entirely up to you. I'm going to show you how I might stay organized. I'm not always successful in staying organized, but it is worth trying to stay organized as much as possible. This is not only for your examiner who's going to be reading your work, but this is for you as well, so that if you've done some calculations, you can quickly and easily retrieve the information that you've already calculated. Okay, so what we're going to look at is the motion before the first bounce. Okay, forgive my writing. And okay, we're going to be looking at the vertical direction, and probably not so. In fact, I don't think we need to look at the horizontal motion. I'll just write it over here, just so you can get an idea about how I'm going to kind of carve things up, how I'm going to organize things. So this is something that I tend to do if I do split motion up when we've got projectile motion. I split things up into vertical and horizontal, and I make sure that I keep these kind of separate in some way. So, okay, we're going to be using SUVAT then. So SUVAT. We might not need all of these things, but I tend to write them out anyway. So then I can just summarize all of the information that I have. So S is going to be h meters, and bearing in mind we're taking downwards as positive, so h is going to be positive. U is equal to 0 meters per second, because remember that the ball is particle, whatever it is projected horizontally, right? So it's got no vertical component. Well, no, it's got a 0 vertical component. Not that it's got no vertical component. It's just a 0 vertical component. Acceleration is going to be g meters per second squared, and do use g rather than 9.8, because if you notice in the formula for d sub n, g is something that appears, and v is something that we're wanting to find. Okay, so which calculation do I want to do? Well, it's going to have to be v squared equals u squared plus, let me get rid of that, plus 2as, okay, which is going to be, in this case, v squared is equal to, that's awful, isn't it? You can tell I'm a novice at this. Is equal to 2gh, and therefore v is equal to the positive square root of 2gh. So this v equals 2gh is the vertical speed before, so immediately prior to the first bounce. Okay, horizontal, we don't really need to do anything with that, to be honest with you. And time, I'm not actually interested in that right now. Okay, but this is going to be important because this is going to follow through. This is I'm going to be able to use the vertical speed before the first bounce to figure out what the vertical speed is going to be after the first bounce. So let's do that now. Okay, so we're moving on now to the motion between the first and second bounces. All right. Again, this is how I might organize my work. And we've got the vertical direction, and we are going to be looking at the horizontal direction here. So I'll write that over here, and I'm going to need quite a lot of space. So in the vertical direction, what's going on in the vertical direction? Well, we've got this coefficient of restitution, which is E, and the coefficient of restitution is speed of separation over speed of approach. In this context, though, it's going to be the speed after the first bounce divided by the speed before the first bounce. Okay, so speed after the first bounce over speed before the first bounce. If you can't read my writing, unlucky. So the speed after the first bounce, is therefore going to be equal to E times the square root of 2gh. And bearing in mind as well that that is going to be in the upward direction. So if we go back to our diagram, we don't really need to actually, but what happens when a ball bounces on the ground? Well, it bounces up, right? So if we're taking downwards as positive, then this particle, as it bounces up, after the first bounce is going to be moving in the negative direction. Okay, so we've got to bear that in mind when it comes to using our SUVAT calculations. Oh, I've gone a bit far there, haven't I? Okay, so now we go on to SUVAT. S-U-V-A-T. S is equal to h meters. U is equal to minus e square root of 2gh. V is equal to, that's something that we're going to need to figure out. A is equal to g meters per second squared. T is equal to, that's something that we're going to need to figure out as well. Okay, so let's have a look. V squared equals u squared plus 2as again. So we get here v squared is going to be equal to 2e squared times 2gh plus 2gh. So v, with a little bit of simplification, is going to be square root of 2gh times the square root of e squared plus 1. Okay. And therefore, using now v equals u plus at, we get that the square root of 2gh square root of e squared plus 1 is equal to minus e times the square root of 2gh plus gt. And rearranging this, you will get that t is equal to the square root of 2h over g times, in brackets, the square root of e squared plus 1 plus e. Okay, so therefore now moving on to the horizontal direction, remember that the speed in the horizontal direction is constant, so we don't really need to use the full SUVAT. We can just use effectively speed equals distance over time rearranged. So we get that the distance d1 is equal to u times this expression for t that I've just found. So it's going to be u square root of 2h over g times square root of e squared plus 1 plus e. Perfect. So what I want to do at this stage is actually check that my expression for d1 coincides with the this expression for d sub n that I've been given. That if I replace in this general expression for d sub n, if I replace n with 1, the formula that I'm aiming for actually agrees with the formula that I've got here, because then that's a big clue that things are going in the right direction, that I'm doing the right sorts of calculations. If you've been given something to aim for, use it. Use it to your advantage. Okay? Now you might say, oh, well, you know, what if I haven't been given an expression to aim for? Well, you know, if things are different, then things are different. You've got to do something different. But if you have been given something to aim for, just use it to your advantage, because you can use it to inform you that whether you're on the right tracks or not. So, okay, let's have a look. So alpha sub n, not alpha sub n, I want alpha sub 1. I want to choose a specific value for it. Alpha sub 1 is equal to, according to this formula, this definition, it's going to be 1 minus e squared, so n is equal to 1 here. 1 minus e squared over 1 minus e squared to the power of a half, which of course is just equal to 1, right? Cancel, cancel. Alpha 2 is equal to 1 minus e to the 4th over 1 minus e squared to the half. Now 1 minus e to the 4th is 1 plus e squared times 1 minus e squared, and so therefore we end up with 1 plus e squared to the power of a half, or in other words, the square root of, oh, that didn't go very well, did it? The square root of 1 plus e squared. Oh, that's even worse. Never mind. Okay, so if I look now in my brackets here, what have I got? I've got alpha 2 plus e times alpha 1. Right, alpha 2 is square root of 1 plus e squared, or square root of e squared plus 1, whichever you prefer, plus e times 1. Alpha 1 is equal to 1. Well, that's exactly what I need, right? According to the formula dn, d sub n, d1 is equal to u times 2h over g to the power of a half times e alpha 1 plus alpha 2. That's exactly what I've got. So my formula, d1, matches what it should be. Okay? Now, at this point, you might feel that you're ready to actually attack the general formula for dn. I personally didn't feel that I was ready at this stage to go for dn. I wanted to continue up to the time of the second bounce, because I didn't feel that I had enough of a pattern there in mind as I was looking at this, to see how this formula dn was going to come about. If you've got the pattern, if you can see the pattern, then that's good for you. Like I said, this is not meant to be a model solution. This is not me saying this is how you have to solve this problem. This is not about getting marks or anything like that. This is just about going through the problem solving process. Whether or not you're in an exam is kind of beside the point. Okay, so now we need to be looking at the motion between the second and third bounces. So once I've done this, then I felt like I was in a position to actually start finding an expression for dn. But also the formula that I've just found for d1 is going to play a role further down the line. So it's not futile. It's not without reason, or it's not without purpose that I've kind of done what I've done, it turns out. Now, this is what I'm about to do now. The motion between the second and third bounces is, whichever way, depends how you look at it. It might be suited, it might be appropriate, it might not be. I did it anyway, but I would argue that you definitely need to find an expression for d1 for this. At least the way that I went through the solution to this problem requires an explicit calculation of the expression for d1. Okay, so the motion between the second and third bounces. So we're back to, we just repeat, basically, rinse and repeat what we've just done. E, which is equal to the speed immediately prior to the second bounce. Which way around is it? Sorry, the speed immediately after the second bounce divided by the speed immediately prior to the second bounce. In other words, the speed, and again in the vertical direction, speed after second bounce is going to be equal to it's e times, what was it? E times this expression here. So it's e times the square root of 2gh times the square root of e squared plus 1. So now we can get on with the suvat. Again, remember that this is going to be up in the upwards direction. Particle or whatever it is bounces upwards. So we've got suvat, and here I've not written it in, but this is dealing with the vertical direction. Suvat, s is equal to h meters. U is equal to minus e square root of 2gh square root of e squared plus 1. V is what I want to figure out. A is equal to g meters per second squared. And T is something that I could figure out. I don't think I actually bothered. Let me have a look. Did I figure it out? I don't think I actually bothered to figure out T. I didn't need to. No. So I'll put a question mark there, but I don't think I'm actually going to bother figuring that out. So again, V squared equals U squared plus 2AS. So this is going to be E squared times 2gh times e squared plus 1 plus 2gh, which is equal to 2gh e to the 4th plus e squared plus 1. So v is equal to the square root of 2gh times e to the 4th plus e squared plus 1 to the half. Okay, so that's the speed immediately after the second bounce. So at this stage now I feel that I'm in a position to do what I need to do, which is an induction argument. Because let me just summarize what the information that we've got now. So just let me, I just need to check something. Speed. Immediately, so what was that? That was the speed immediately prior to this. I'm just, right, okay. So what we're seeing here is, that I think that the speed immediately prior to the nth bounce is equal to the square root of 2gh times, and it's the sum of so this was the speed immediately prior to the third bounce. So it's e 2k minus 2, k equals 0. Right, okay, k equals 0 to n minus 1 of e to the power of 2k to the half. Okay, that is my kind of hypothesis. So this is me taking a bit of a guess now at what I think that the general formula is going to be for the speed immediately prior to the nth bounce. We can also figure out a formula for the speed immediately after the nth bounce. Immediately after the nth bounce, which I suspect I'm going to prove this, by the way, is going to be 2gh times the sum from k equals 1 to n of e to the power of 2k to the power of a half. Okay, hopefully I've written those down correctly, but it's really this this one here that I'm wanting to concentrate on, the speed immediately after the nth bounce. Okay, so let me scroll down a little bit. So we're going to start an induction. Okay, an induction argument. So use induction, and it's going to be on that speed immediately after the nth bounce that we're going to be using induction on. So we need a base case. So, okay, want to prove. Let's make it clear what we want to prove. We want to prove that the speed after the nth bounce is equal to the sum from k equals 0 to square root of 2gh, the sum from k equals 0 to n of e to the 2k to the half. Okay, that is what I'm wanting to prove. Okay, so what's the base case? Obviously, when n equals 1. What did we find? When I actually went through this calculation, the speed after the first bounce, immediately after the first bounce, was e square root 2gh. Okay. So I found it to be e times the square root of 2gh. And I think I might have made an error actually. I think sorry, it should have been k equals 1 in here. The sum should start from k equals 1. Well, this happens to be equal to the square root of 2gh times the sum from k equals 1 to 1 of e to the power of 2k to the half. So the formula is valid when n equals 1. So the base case, n equals 1, tick. Okay. So this is perfectly fine, by the way. I know typically you may be used to using proof by induction in a pure maths context, but there's no reason why you can't use proof by induction to prove results in mechanics as well. For all intents and purposes, the mechanics part of this is it's over very quickly, and it really just does become algebraic manipulation, as is usually the case with a lot of mechanics problems. The mechanics part is over very quickly, and you just get into just, like I say, algebraic manipulation, just messing around with algebraic expressions and things like that. So now, assume for some fixed n that the speed after the first bounce, I'll call this Pn, by the way. So this expression here is going to be Pn. So here we've got, for example, that P1 is true. Assume for some fixed n, Pn is true. Okay, so now I just do my suvat, okay? So that's the speed after the nth bounce. So suvat, let's scroll down a little bit so I've got a little bit more space. So suvat, s is going to be h meters per meters. Acceleration is g meters per second squared. U is equal to minus root 2gh. The sum from what was it, k equals 1 to n of e to the 2k to the half. V is equal to question mark. Okay, so v squared equals u squared plus 2as. So we get v squared is equal to 2gh times the sum of e2k from k equals 1 to n plus 2gh, which is equal to 2gh. So what I'm hoping to show here is that if Pn is true, then this implies that Pn plus 1 is true. Now, the reason that, just to be clear, the reason why I've chosen to do induction on this particular expression is because I can get the implication that I need. Okay, you might think, well, why don't you do induction on d sub n instead? Because I can't. I tried to run it through in my mind, and I could be wrong, but I can't see how I would get the implication that I need, unfortunately. So it turns out that this, for me, seemed to make more sense. Do the induction on the speed immediately after the nth bounce, and the result follows easily from this. But I'll explain that as we get there anyway. So this is the sum from k equals 0, that's k equals 1 to n of e to k plus 1. Okay, so then t is going to be equal to, remember, it's v minus u over a. So I'm cutting out a little bit of the detail here, but we're going to get square root of 2h over g times the sum from k equals 1 to n of e to the 2k plus 1 to the half minus that will be plus because u is negative. The sum of from k equals 1 to n of e to the 2k to the half. Okay, scroll down. Which is equal to the square root of 2h over g actually I don't need to be, what am I doing here? I don't actually need to be doing this just yet. Let's just park that for a second. I'll come back to that. It's actually this, I've gone a bit too far. In fact, okay, let's just get rid of that actually. Sorry for that. Because this is the speed immediately prior to the n+1th bounce. So to find the speed after the n+1th bounce, the pattern is that I just multiply this by e, the coefficient of restitution. Okay, so the speed after the n+1th bounce is going to be equal to e times this thing, so it's going to be 2gh square root of 2gh e times the sum k equals 1 to n of e to k plus 1 to the power of a half, which is equal to 2gh the sum from k equals 1 to n of e to the 2k plus 2 plus e squared, which is equal to the square root of 2gh. So just shifting the k effectively. So I'll just change it to make it a bit clear. From r equals 1 to n plus 1 of e to the 2k, e to the 2r, sorry. Oh, forgot my half. So just to be clear, as I've gone from this expression to this expression, I've replaced the k with r effectively. So r is equal to, what's it going to be equal to? K plus 1 or something like that. I could have stuck with k and just replaced k with k plus 1. Okay, but that's the formula that I needed, right? That's the formula that I wanted to prove. That's effectively Pn plus 1. So Pn was what? Square root of 2gh, the sum from k equals 1 to n of 2k, e to the 2k to the power of a half. We've got here the sum from r equals 1 to n plus 1, e to the 2r to the power of a half. So this is Pn plus 1. So in other words, we've got Pn, P1 true. Pn implies, P Pn true implies Pn plus 1 true. So by principle of mathematical induction, Pn is true for all n is a natural number. Okay. So a bit of a messy induction, but now once we've got that, we can find our. We know then that these expressions that we've got for the vertical speeds, things like that between the bouncers, they all follow this particular pattern, right? So if we look at the motion now, motion between the nth and n plus 1th bouncers, then we know using SUVAT, S-U-V-A-T, we know that S is going to be equal to h meters. U is going to be equal to, let me get it right, speed after the nth bounce. Right. So it's going to be this minus, don't forget the minus square root of 2gh. The sum from k equals 1 to n of e to the 2k to the half. V is what we want to find. Acceleration is g meters per second squared, and we're also going to need to find t. Okay, t equals t, whatever. So v squared equals u squared plus 2as. We've kind of already done this, haven't we? We found that it's, where is it? Speed out. 2gh, yeah, okay. So v squared is 2gh. The sum from k equals 1 to n of e to the 2k plus 1. Okay. So this is where I started getting a bit ahead of myself. This is where I need to find the value of t. This is what I started doing before that. I started getting, yeah. T equals v minus u over g. So what we get is the square root of 2h over g. The sum, k equals 1 to n of e to the 2k plus 1 to the half, plus the sum from k equals 1 to n of e to the 2k to the half. Okay. Oh, get rid of that. Right, which I can write as 2h over g, and you'll see why I'm going to write it like this in a second. E to the 2k from k equals 0 to n plus sorry, no, just n. Yeah, no, I can stick with that. To the half plus e squared, or e times the square root, yeah, the square root from k equals 1, k equals 0, sorry, to n minus 1 of e to the 2k. Now, why have I done that? Why have I written these expressions in this particular way? The answer to that is as follows. If we look at alpha n, which is 1 minus e to the power of 2n over 1 minus e to the e squared to the half, this is equal to 1 minus e squared to the power of n over 1 minus e squared to the half. And now, if we use the relationship, the formula that 1 over... no, sorry. So this is a little aside. 1 minus x to the power of n plus 1 over 1 minus x is equal to the sum of 1 plus x squared plus all the way up to x to the power of n. In other words, the sum from k equals 0 to n of x to the power of k. Okay, so this is a really useful formula to know. So how would you do this? Well, I'm sure you've probably come across this as part of your... I don't really want to get into how you prove this, but well, I mean, really, you could just think about multiplying out 1 minus x times 1 plus x squared plus da 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 up to xn, and show that you get 1 minus x to the power of n plus 1. So it's not going to be too difficult. But this is the formula that we're going to be using. So effectively, if we think about the x replaced with e squared, what do we get? We get the sum of, from k equals 0 to n, is it going to be n? It's going to be n minus 1, sorry, of e to the 2k. Okay? So this formula here is, well, actually including the half as well. So let's just make that a bit clear. This formula here is effectively alpha n plus 1. Notice that alpha n and n minus 1 here. So because we've got n as the upper limit of this sum, that means that this is alpha n plus 1. Right? The upper limit of the sum is 1 less than the subscript of the alpha. And therefore this one here is going to be alpha n. So here we've got alpha n plus 1. Here we've got alpha n. So in other words, clear a bit of space. We've got t is equal to the square root of 2h over g. Now let's have a look again what we had, just so I can remind myself. I want to get it right. So it's alpha n plus 1 plus e times alpha n. Okay, so e alpha n plus alpha n plus 1. That's the time between the nth and n plus 1th bouncers. So the horizontal distance travelled, remember speed u is constant, the horizontal distance travelled is going to be dn, which is equal to ut, which is equal to u 2h over g to the half e alpha n plus alpha n plus 1. Perfect. We've done it. Okay. So we've proved this formula. So it's taken a while to get there, but I've been explaining, describing what I've been doing at each stage. Hopefully you understood that. If there is anything that you're not clear about, then, you know, by all means, just drop me a message or whatever. We're not done yet, so we've still got another part of this problem to go. You'll love to hear. Okay, so the fun's not over yet. But the next part's not too bad, really. It's not too difficult. So, if n is very large, show that u must satisfy this equation. U is equal to, what is it? L squared g over 2h to the power of a half. 1 minus e over 1 plus e to the half. So, what does it mean for n very large? Well, in mathematical terms, if n is large, that means that n is effectively approaching infinity. Okay. Generally speaking, in mathematical terms, when you talk about something, a number being small, especially in say analysis, in real analysis and things like this, when you're dealing with sequences, that means that it's finite. Okay, so even though the number might be in the billions or the trillions or the trillions of trillions of trillions, that's still small when it comes to considering the infinite. Okay, so what we're looking at here is effectively what happens when n approaches infinity. Well, one thing that we know, if n approaches infinity, and also if e is less than 1, is that e to the power of 2n is going to approach 0. So let's have a look at our formula for dn. So dn, what happens to dn as n approaches infinity? Well, in fact, before we do that, let's have a look at what happens to alpha n. So alpha n, as n approaches infinity, is going to approach 1 minus 0 over 1 minus e squared to the half, which is what? 1 over the square root of 1 minus e squared. So dn is going to approach, as n approaches infinity, u times the square root of 2h over g. What was it? E alpha alpha n, which approaches 1 over square root of 1 minus e squared, plus alpha n plus 1, which also approaches 1 over square root of 1 minus e squared. So that's equal to u times the square root of 2h over g, e plus 1, over the square root of 1 minus e squared. So that's going to be square root of 1 minus e times the square root of 1 plus e. Have I missed off? No. Which is equal to u times the square root of 2h over g. And do show all your working, by the way. It's a bit of a pain having to write all of this stuff out, but do show your working. So we e plus 1 and square root of 1 plus e, there's going to be some cancellation there. So we're going to square root of 1 plus e over square root of 1 minus e. So that's going to be equal to u times the square root of 2h over g times 1 plus e over 1 minus e to the half. Well, these are all constants in here. U is a constant, h is a constant, same height for the stairs, g constant, e constant. So this is equal to a constant. So in other words, dn becomes effectively constant as n approaches infinity. It gets closer and closer to this particular constant. So remember what we were told right at the beginning of the problem. The particle falls down the staircase, bouncing once on every stair. Okay, bouncing once on every stair. So assume now that this constant that we've got here, that the length of the stair, the width of the stair, whatever, is slightly shorter than the limit that dn approaches. That means that eventually, because there's going to be so many of these stairs, eventually dn is going to be, it's going to bounce right on. I'll just draw a diagram. We've got our stairs. So let's say that L, the length of the stair, is less than the limit of dn. Okay, so the limit as n approaches infinity of dn. Then what's going to happen? At some point, this particle is going to bounce really close to the edge of this top stair. I'll do it in red here. And it's actually going to bounce straight over the edge of this stair here. It's not actually going to bounce on this stair. It's going to bounce down here. But that's forbidden, because we're told that the object bounces on every stair, once on every stair. Okay. Similarly, similarly, if our ball, if the length of the stair, L, is now greater than the limit as n approaches infinity of dn, what's likely to happen at some point is the particle is going to kind of bounce really close to like the corner of the stair, and then because L is greater than dn, when the ball bounces, it's actually going to bounce a second time on that stair. So this might happen. I mean, we're told that n is large, so we're allowing n, uppercase N here, to be as large as it needs to be for this to happen. This is what we're talking about when I'm saying that it effectively goes to infinity. We allow it to go as far as we want it to go. So this is eventually going to happen. But this is forbidden. The particle bounces once per stair. So what's the upshot? It means that L must be equal to the limit. L must be equal to the limit as n approaches infinity of the dn, which is equal to the square root of 2h over g times, what was it, 1 plus e over 1 minus e to the half. So therefore, rearranging this, what do we get? We'll get u is equal to the square root of gl squared over 2h times 1 minus e over 1 plus e to the power of a half, which is exactly what we needed. Okay. So that brings us to the end of this particular problem. So this has been a fairly long video, I've got to say. It's been a difficult one for me to make. With this being the first time that I've used this, all of this stuff. But let me know what you think, whether you found this video useful, whether you found the actual presentation of the video useful, or if there's anything else that you think I could be doing better. Because I really want to continue making these videos, and I want them to be helpful. I really want to help you prepare for your STEP exams, prepare for your MAT exams and your A-level maths and further maths exams. But for me to do that effectively, I need to know what it is that you want help with. So I'm quite happy to continue making these videos. I don't make any money from these videos, by the way. So it would be great if you could show your support for this video, on this channel, and encourage me to keep making these videos by hitting the subscribe button and hitting the like button. And also, if there is anybody that you think might benefit from these videos, please pass these videos on to them. I really would like to continue making these videos, but I can only justify it because they take such a long time to make and prepare and everything. I can only justify it if there is actually support for it. I don't expect any payment for the videos. I would like to make them freely available. I don't really want to have to put them behind a paywall or anything like that. So I would like to make them freely available, but I can only justify that if there is actually support for me to make them. So it would be really good if you could hit the subscribe button and give me some feedback. Hopefully positive feedback. If you think the video's crap, tell me. But tell me why it's crap. Don't just say it's crap. At least tell me why it's crap so I can do something about it. But, okay, I think that's enough for this video. Let me know what you think. And if you've got any ideas about other things that I could cover in my videos, let me know. But I'm going to go and have something to eat now because I'm absolutely starving. So that brings us to the end of this video. Thank you very much for watching, and I'll see you in the next video. Cheers, guys.